All right, people. There we go. Hey, everybody. What's up? All right, today we're going to talk about thermodynamics. We're going to talk about what heat is, how heat goes from one place to another, and how different objects hold heat and respond to heat. There's going to be a lab. For those of you at home, I hate that you're going to have to just watch the lab, but the lab that we're going to do today, eventually on an ed puzzle, is a pretty good lab, all right? So I'm going to zoom in here really tight so you guys at home can see the slideshow, okay? All right. I think that might help it show up a little bit. Okay, first thing. We're talking about thermodynamics, all right? That means the motion of heat or the changing of heat. Thermo is heat, dynamic is motion or changing or the dynamics of the system, okay? So obviously there's the first law of thermodynamics. That's just like the first law of anything, and that is that heat isn't really created or destroyed. It just moves from one place to the next, right? So if you had something hot, like a hot iron, and you put it into cold water, you didn't kill the heat or make the heat that was in the iron disappear. You gave the heat to the water, right? So anytime you see the first law in science, it's like cannot be created or destroyed, right? First law of energy, first law of thermodynamics, first law of matter, first law of mass, all those things cannot be created or destroyed. Does that make sense? All right, now the second law is a little more unique. The second law is called entropy, and entropy is disorder. Disorder in a system. And that's a cool word, and that's a cool term, and you've never heard anything like this in any of your other classes. But the entropy of an isolated system never decreases, okay? And such a system will spontaneously proceed towards equilibrium, the configuration with the maximum entropy, okay? And here's what this says in the quickest way a teacher could put it. If you have a bunch of heat in one place, that heat is going to spread out and become as disorganized as possible. If you have an ice cube and you put it in hot water, then what you have there is an organization. You have a colder spot and you have a different spot where all the rest of the water may be warm. Well, the ice cube is going to melt and all the heat will spread out. All the temperature everywhere will become the same. That's what naturally happens. That's entropy. If you don't want to think about it as heat, you can think about it as, hey, if I drop a glass on the floor, it's going to shatter into randomness. It's not going to spell out oops and little shards of glass. I mean, maybe 1 in a trillion times it could do that, and that'd be pretty sweet. But that's not entropy. Entropy is disorder, all right? So a couple things that you might not think about, but food is something that stores energy, okay? And I know this is a bit of a rewind, but the sun shines on a plant. That plant takes the sun's energy and organizes it into sugars, and then you take that energy and put it in your body, and then you use it for motion, okay? Now, the storage place where we store energy is in food. Food stores energy, okay? And then now we can talk about what a calorie is, because we'll use this later in the lab. A calorie is the amount of energy that raises 1 gram of water by 1 degree Celsius. Hey, cut that off for right now. Kids at home, we have some boiling water here in the classroom that we're getting ready. Keep yours going until it boils, okay? And then cut it off when it boils. We're going to try to keep it right there so we can use it. Does that make sense? All right. And 1 calorie is equal to 4.18 joules, all right? So you want to jot that down, or you can realize that it's on page 1. Now, I seem to be talking about different things. calories, entropy, disorder, but I'm not. Sorry, my mask is itching me to death, y'all. It's itching me to death. Maybe I got it that time. But really, I'm talking about one thing. I'm talking about heat. I'm talking about energy, how it's stored, how we measure it, how it's used. Now, this leads us to the point of the lesson. And the point of today's lesson in today's lab is specific heat. Specific heat for a substance is the amount of heat required to raise the temperature of 1 gram of any substance by 1 degree Celsius. We call the specific heat of water a calorie. Okay? But we have a specific heat of all things. I'm going to show you. Here we have, here is 70 grams of aluminum, okay? This is 70 grams of aluminum, and I know this looks like less, but it's still the same thing. This is 70 grams of copper, and this is 70 grams of lead. And the thing is, they're all equal in mass, all right? Now, if you had a heat lamp or the sunshine and you shined it on this, all 3 of these objects for 30 seconds, and then you touched them, they would feel like they were 3 different temperatures. Why? Because they absorb heat and they release heat at different rates, okay? It takes more energy to heat up the aluminum than it does to heat up the lead. Now, how would I know that? Well, I could look on the front of page 1. Everybody flip to page 1 in your chemistry table. I'll put it on the screen for the people at home. So, if you're at home, look right here on page 1. At the bottom of page 1, you see specific heat. Look at the specific heat of aluminum. It's 0.897 joules of energy per every gram to raise aluminum 1 degree Celsius. So this aluminum's pretty hard to heat up. Now let's look at the lead. Everybody see the lead? Lead is right here on the bottom of page 1 again. Lead takes only 0.129 joules. So it is 7 times harder to heat up aluminum than it is to heat up lead. And we're going to prove that today in a lab. Now there's a formula for this, obviously. There's a formula for how much energy it takes to heat up all these different substances. And that's why they give you these tables on your reference tables. That's why they give you the table of specific heat, so you can do some calculations with it and you can understand it. There's a formula, and the formula is super, super simple, okay? Now, you saw a video yesterday on specific heat with veritasium. If you haven't seen it, I'll release it. And here is our formula that I want everybody to write down. It is Q is equal to CMT. Q is equal to CMT. And I'm going to write it down myself. And we'll work a couple of problems, and then we'll end our little quick video lesson here, okay? Q is equal to CMT. And hopefully one of my markers will still work. Q, there we go, is equal to, I usually say MCT, okay? Does your reference table give you the formula in any specific order? Because I'll use the same order that the reference table uses. Let's look on our reference tables. Go down here.
It says Q equals
Yeah, MCT, okay. All right. The reference table looks like this. Q equals M, C, big old C, with a little letter here, P, and then delta T, okay? Now, I'm going to explain to you what each one of these things means. Q is a letter that we use to represent the energy. And what is energy measured in? I've mentioned it several times. Anybody know what units energy is measured in? Joules, that's right. Excellent. Calories, we can use calories for water. Joules. So Q is the energy in joules. I guess that you know what M is going to be, right? What do you think, Maisie? What's the M? That's right. M is going to be the mass in grams. And then what do you think T is going to be, Evan? Yeah, and does anybody remember what delta means? It's a simple math term. You've probably heard it before, but delta means the change in. So this is change in temperature. All right? And then C is the specific heat. The letter C is the specific heat, and that is just the number that you look up on your table. That's all there is to it. That is just the number that you look up on your table. Does that make sense? For example, the specific heat of aluminum is 0.897, right? The specific heat of lead is 0.129. Here, I'll put this up. So when we talk about specific heat, for aluminum, it's 0.897. And if we were talking about the specific heat of lead, that would be 0.129. So this is the letter C. Now you may say, Mr. Perkins, what would one of these math problems look like? And I'll show you very quickly. All right, a long time ago, someone took a metal triangle and they set it on a wood stove, okay? And they used it to do some work at their house. All right? Now, this triangular-shaped chunk of metal held heat, held a good amount of heat, so it would stay hot for a little while. The specific heat of this amount of metal was of this type of metal was 0.449. Okay? And you usually had about a kilogram of this metal shaped into a triangular shape. So for mass, we're going to put 1,000 grams. Okay? Everybody with me? Now, if you put it on the stove until it was very hot, right? Until it was very hot. Let's say you heated it up to, say, 100 degrees Celsius, and then you used it until it was room temperature. What would that change in heat be? You would say 100 degrees Celsius minus 100 degrees down to 23 degrees. What would the change in temperature be? 77. So if you heated this chunk of metal up to 100 degrees and then you used it until it was cool, right? And it wouldn't cool past room temperature, would it? That's the law of thermodynamics. And you used it until it was just room temperature, then the change in temperature for that substance would be 77 degrees, And remember, this doesn't matter if it's Kelvin or Celsius, because Kelvin and Celsius degrees are the same size, right? Right? Then how much energy did you get from that chunk of metal? How much energy was used? You got that energy from the wood stove, and then you use that energy to do some work. The amount of energy you use would be 1,000 times 0.449 times 77. So you take your calculator and you multiply those three numbers. 1,000 times 0.449 times 77 equals, you use 3,457 joules of energy. Now, I've been talking about this crazy, wacky, triangular-shaped chunk of metal and doing work with it and putting it on a wood stove till it got really hot and then using it. Can anyone at home or in this classroom, before we sign off on this video, can anyone tell me what type of metal this was that 100 years ago someone would put on a wood stove? It's shaped like a triangle. They would get it hot and then they would use it to do work until it was room temperature. You are smart. It's an iron, people. That's what ironing is. And that's why ironing is called ironing, because you literally just heat up a chunk of iron and rub it across. Now your iron's made out of aluminum, right? But have you ever thought about why is it called ironing? Because it's just a chunk of iron. The specific heat of iron is point. Now, did you know it from my story, or did you realize that the specific heat was 0.449? Well, that's good. All right. People at home, I'm not going to try to do my cool peace out because then I can never hit the button and turn it off, so I'm just